Hello, Earth Science students. Hey, welcome. Thank you for opening this up. Thank you for beginning your educational journey, and I really appreciate you being a part of this. You're watching this, so it's officially week 2 of the school year. We had that first week of kind of getting to know each other, learning the basics, Google Classroom, where to go, what to do, when to do it, how to do it, all that kind of good stuff. So now we kind of really start the meat and potatoes, the real deal on the school year. But before we do all that, again, thank you for being here. Thank you for starting your process, and hopefully you're well. This video, as you can see, is made August 22nd, so it's actually a redo. I'm not sure what happened to the first one. It just wasn't there when I started to upload them to everything. But that just means it'll be better than the first time, because they'll have a more full understanding of what we're trying to get done. So anyway, with that in mind, we will get going. Hopefully, watching this, you're at home, you're at a friend's house, you're on a road trip with your family, whatever, and you're just getting this out of the way. But hopefully you will enjoy the benefits of watching these videos, in the comfort of your own place, wherever you choose to, back porch, who knows, who cares. But that you enjoy the benefit of doing it in your own time, in your own. Maybe you've got to work around your work schedule. Maybe you've got to work around your family schedule. Maybe you've got to work around a sports schedule. Who knows? But that you have the opportunity to do so whenever you want, and that you don't have to sit in the classroom. Will I stand up front? Or in my case, my lecture style usually was just move around the room. But anyway, you don't have to sit through the full lectures in the classroom. You can write your notes at your own pace. You can pause this. Hey, you get sleepy, you get tired, you can stop and go do something else. Watch a little Netflix, play a little video games, whatever you do. Watch a little sports that you can watch on TV. You just can't go there and watch them. But anyway, that you just enjoy that, and that that's helpful to you, and the benefits from that. So with that, we'll get started. One last thank you, and let's get your educational journey underway. Well, as you can see on your screen, we're dealing with wavelengths. Okay, and we've got to, the whole unit is the sun, moon, and the earth, and all those relationships. But to fully understand what the sun provides for us, we've got to understand the electromagnetic spectrum. We've got to understand how wavelengths work. And we're going to throw in a little bit about why radio waves are good or okay. They're not dangerous to us. And why X-rays and gamma rays and that stuff are dangerous for us. So let's begin that process. I am, let me get a pen here. Since this is sun, moon, and earth, let's go with the nice green. Represent the earth, plus we'll throw in a Hulk reference every now and then because of our good friend the gamma rays, and we'll throw in a little cultural historical perspective, taking you back to the 1970s and probably even earlier than that with the comic book versions. But anyway, so we will have a full spectrum. I needed to add that these are trying to replace lectures into videos. And for earth science, typically what we've done is talk about something for about 15 minutes each day, and then do some things in the classroom to reinforce those. So if 15 minutes a day, that's 75 minutes for the week, which this will not be that long. But what we'll add to that is not only me talking about it, but you pausing it to excuse me, to take your notes and stuff. So we're going to try to recreate that 75 minutes So about 40, 45 minutes of me talking, 20, 25, 30 of you kind of pausing it and writing down things, or pausing it and go to the restroom, whatever. And that'll be our 75 minutes. So, but to fully understand what the sun provides for us, we've got to understand the electromagnetic spectrum. But hopefully, in your middle school years, someday, at some time, you guys touched on this, and hopefully in your physical science year, you touched on this. So hopefully this is your third look at the magnetic spectrum. So we won't go deep. We will just kind of cover the introductory and go from there. So now everything on this line is the same thing, just different versions, and we're going to pull a little bit out of each one of them to kind of get a full picture of the electromagnetic spectrum. Now, being high school students, this will be part of your grade. So essentially, as I explained in the classroom, the way this will work, over the weekend or whenever, just prior to us talking about it, you'll watch these and you'll take the appropriate level of notes. And then when we get back on Monday, I'll ask to see them, and then your grade will be based on your amount of notes, your percentage of what you should have. So it'll be worth 25, and so if you have half of what you should have, then you'll get 50% of the points. If you have 3/4 of what you should have, then you'll get 75% of the points. If you have all of it, you'll get 100%. And as I go through here, I will clearly identify what I would like you to have and to draw. With the bio students and the A&P students, they have a lot of notes. In some drawings, you'll have some notes and probably more drawings because it is earth science. You can already see a telescope. You can already see the magnetic spectrum. So things like that. So just if I identify it, be sure you have it on your paper when I ask to see it. So with that, let's get started. So we are talking about the electromagnetic spectrum. The electromagnetic spectrum is simply these, it's like a packet, or think of it as in electronic devices, it's a zipped file. You know what a zip file is? It's a zip file, and when it gets to Earth, okay, this zip file is opened up, and you have this wide range of materials, and I'm using air quotes, which you cannot see. Materials anywhere from, all this stuff, anywhere from wavelengths that are converted to radio waves, microwaves, infrared waves, visible waves, ultraviolet, X-ray, gamma ray. Those types or categories. Now, so this energy packet arrives at Earth, and these different types are different because of their wavelengths. So let's talk about wavelengths, and we're going to do so. We'll use this one, and then you can see these wavelengths kind of in this diagram here, and it's also right here, and it's also right here. So a wavelength is simply, you can see it right here, a wavelength is simply the distance between two crests, and you can also do it, difference between two troughs. So these are crests, okay, these are troughs, which means the bottom, okay, and you can see the word crest here and trough here. That is a wavelength. The further apart that wavelength is, the less energy. Okay, the closer those wavelengths are, the more energy. So if we look at our two examples here, okay, we're going to put the word more and of course I'm writing with my cursor, which looks like my penmanship is bad, less, and then we'll just put a big E out here, and the E represents energy. So shorter wavelength has more energy, longer wavelength has less energy. It's like, say you've got this friend and he punches you in the arm. It's not super hard, okay? It's something you can take. You know what's happening, okay? But he does hit you in the arm. Now a longer wavelength, say he hits you in the arm once every 5 minutes. Okay, it's not super hard. You know it happened, and maybe, okay, but it never really back up. Never really causes you any damage. Okay, now, so that type of wavelength would be like a radio wave. Okay, it happens constantly, all the time, but it's not enough to cause any concern or damage. Now let's say we reduce that time from 5 minutes to 1 minute. Okay, now the punch happens every 1 minute. Now we've gone from being a radio wave, now we're like an ultraviolet wave. Okay, based on your amount of muscle or layers in your deltoid, which is your shoulder muscle. It may cause damage. Okay, it may not cause damage. If you've got a lot of muscle or you're just a big person in general, you still feel it, but it may not cause you any damage. But if you're a smaller person, maybe it does hurt after a while. Maybe it does leave a bruise. So if you think about UV rays, for some people, they are a danger. Others, maybe not so much. So there's just other factors at play. Okay, now let's say we make that the punch happens every 30 seconds. We've gone from 5 minutes to 1 minute. Now we're at 30 seconds. Okay, now we've increased the intensity. We've increased the frequency. And now we've made it similar to an X-ray. Okay, now it probably will leave a bruise eventually, and it may even get sore. Okay, and so now we're kind of like X-rays. X-rays can be very dangerous and perhaps deadly to some people. It's just a different level of intensity embarked on your cells, and that's how the wavelength works. We've shortened that wavelength. We've increased the frequency and done that. So now let's take the punch, and now it happens every 10 seconds. So every 10 seconds you get a punch on the arm. Okay, it doesn't matter who we are, that eventually will leave a bruise, will hurt, will affect you physically as that punch comes in, even though the punch intensity itself hasn't changed. What's happened is the frequency of the punch has changed. And that's similar to what would be metaphorically as a gamma ray. Now it is going to cause damage no matter who you are. And so if you think about the word gamma ray, go back to 1970. 1970, I mean, we put a man on the moon. Science fiction is just going crazy with ideas about science and all that stuff, and we've kind of gotten into the idea of the superhero and their powers, and being bitten by a spider, being gone through a gamma ray explosion. I mean, it was just kind of a cool concept, and you think about the Hulk and the whole gamma ray and making it strong and big and angry, and all that just kind of came out of just a little bit of understanding of how this stuff worked, and just enough to know that it would do that to a person. It would change, and they just made that particular situation out to be not necessarily a positive, because Bruce Banner isn't considered a positive, but just that idea of this massive being and of course then made famous in all the Avenger movies, which are just fantastic. So the idea of this, now this particular one here has it flipped from the others. This one has gamma rays on the right. Oh, I guess this one does too. Yeah, so it looks like we're kind of happening. Well, I guess all three of them do. I didn't realize that this is the only one that has it going this way. So just recognize that gamma rays, what end the gamma rays are on. But what we want to look at is this idea of, as we're going from radio waves to gamma rays, whatever direction, the frequency increases and the amount of energy increases. Now the punch doesn't get any harder. It just happens more often. Okay? So if you think about, if I'm digging a hole, if I take my shovel and I get the same amount of dirt out each time, but I increase, in the beginning, I do a shovel load every 10 minutes. Okay, and then I go down to 5 minutes, 1 minute, 30 seconds, 10 seconds. There's just more energy involved in the hole digging process as I increase the frequency. And that's the key there, increasing the frequency. All right, so what you want to get out of all this is, as far as your notes, okay, you want to make sure that you, somewhere on your paper, draw this wavelength diagram where it goes from the radio waves to the gamma rays, and you show that gradual increase in frequency, much like this or this over here. This one doesn't have one, this one has one as well. It's hard to see here because it is green, but just have that wavelength. Okay, what you also want to do, and I've got it circled here, is make a list of the types of categories of the wavelengths, and make sure you have them either above or below the wavelength that they correspond to. So for example, if you draw it like this, make sure you have the names under it just like that. Or if you draw it going this direction, make sure you have the names either above or below that correspond with that. All right, next part. Next thing you want to be sure you have either like this or like this one over here. And if you want to do it this way, that's fine too. But make sure you have a wave drawn and you identify what a wavelength is. Now, you don't have to have this amplitude stuff. That's a whole different thing. If we were going to talk about frequency, not frequency, but pitch or tone, the higher the amplitude is, the higher the pitch. But anyway, we're not associating with that. We're not dealing with that. So, but make sure you have this wavelength diagram and that you identify what a wavelength is. All right. Now, the last thing we'll talk about this, and this also deals with the dangers of the different wavelength. It's this word ionizing, and I have it up here. Ionizing refers to modifying cells. So a TV and radio waves, they do not modify your cells. A X-ray or gamma ray or UV ray, they do, to varying degrees, modify your cells, and that's why they're dangerous to us. That's why they can cause cancer, because they can change. They can change your, in the mindset of cancer, they can turn that cell into a normal reproductive cell, or a normal cell that reproduces in a typical manner, to one that reproduces without the checks and balances that they normally have, and it just replicates, duplicates faster and without any checks and balances, which means continually. And that's where you get those growths, that's where you get that those masses and stuff like that that are associated with cancer. So that's what ionizing means. It can modify the cell. Okay, so you want to make sure you have that reference as well. So far, when I look at your notes, I'm going to look for the wavelength. I'm going to look for the category types. Okay, I'm going to look for the wavelength diagram, and I'm going to look for the ionizing reference. So that's 4 things so far that you want to have on your paper. So while you're double checking that, let me close out the ink tray and slide this up. And our next category, as you can see, is telescopes. Alright, so telescopes, and we actually have 3 categories. We got the EMS, which we just did, and telescopes, and then the application of telescopes. And we're also going to connect it back with the construction of telescopes. So for telescopes, there are 2 types. There are refracting, let me get a pen here, and let's see, do we want to change the color? Yeah, let's go to a nice blue here. I do like the nice blue. So we've got refracting telescopes, and we've got reflecting telescopes. And in refracting, it's also listed right here because that's a comparison slide that we'll look at. So of all the telescopes in the world, all of them are one of these 2 types of telescopes. And the only difference between the 2 is the way they deliver the image to your eye. They work the same way as far as bringing the image in. They work the same way as far as bringing the image to a crisp, clear image. The difference is the way it delivers it to your eye. And we will talk about that. Now, neither one are better than the other. Okay, they just do it in a different way. So it isn't like refracting telescopes would be like what you'd buy at Walmart, and reflecting is what they use in outer space. No, there are some telescopes in outer space that are refractors. There are some that are reflecting. The only clarity there is, what does the scientist want to do? How does it want to bring that image in? And a lot of it is just personal preference or the situation that you may be in, and you've got to use one or the other. So let's start with refracting telescopes. Refracting telescopes is a type where you look in one end and the image comes in the other end. But the way this works is the light comes in and it goes through an objective lens and travels through the objective lens, and that lens, okay, is curved just slightly. Okay, curved just slightly, and you can see it again over here as well. And that bends the image, bringing it all to what we call a focal point. Okay, so it takes this part of the image, this part of the image, this part of the image, and bends them to bring them all to a focal point in a nice, crisp, clear manner. Okay, eyeglasses work the exact same way. Okay, eyeglass lenses are curved as well, and that curve allows the light to be bent to bring it down. And of course, this situation with eyeglasses, your focal point is down to your eye lens in the center of your eye. This refracting telescopes work the same way, and so do reflecting, that you'll see as well, just in a little bit different manner. So they bring it down to that focal point, okay, then it gets delivered to your eye through the eyepiece. Okay, so that's the way refracting telescopes work. So let me close out the ink tray and slide this up so we can look at reflecting telescopes. Okay, and again, pull my pen up here and got my nice blue. Now we're looking at reflecting telescopes. Okay, so the way reflecting telescopes look, and you can see here, let me look. Yeah, let's look at this one over here. Now this one, reflecting, you look into the tube from the top. Okay, and the reflecting and why it's called a reflecting is because it has this mirror in here that sends the image up to your eye. But the light still comes in this way and makes its way to this concave mirror. So refracting telescopes use lenses. Reflecting telescopes uses mirrors. That's why it's called a reflecting telescope. So the image comes in, okay, it hits this mirror, which sends it back, the image back to the second mirror, and then up to your eye. Okay, that's why it's called reflecting. Okay, and you can see it here again. Image comes in, hits the big mirror to the small mirror, up to your eye. And now the focal point is that is a distance in between the secondary mirror or the flat mirror and your eye. That's the focal point. So it uses those two mirrors to kind of just gather everything, all the information as far as the image, and then bring it to that focal point and then up to your eye. So that is how refracting telescopes work. So you already have 4 things to have on your notes. Okay, the 5th and 6th thing to have on your notes is just a little summary, 2 or 3 sentences, 4 sentences if you're going to go crazy. Just describe how a reflecting telescope works in one paragraph, and in a separate paragraph give me a summary, 2 to 4 sentences, how a refracting telescope works. So hopefully I have given you enough information, but if you need more, you can certainly look them up, Google them, whatever you want to call it, ask Alexis, whatever, and get that information. So far we're up to 6 things that need to be on your paper when I take a look at it. Alright, let me close this out. Actually no, because I do need to close it out and bring this down a little bit so we can see the refracting, because I want to use this diagram here as part of my interferometry talk. Alright, so now we're going to talk about this. So this will be number 7. Be sure you have that written down. That'll be number 7. And it will also be your last thing that you have to write down. But let's talk about this interferometry idea and the ways in which we see that in our daily lives. When we go on trips here at Stewart Compound, especially if it's somewhere that we've never been, if we go down to Branson or we go down to Fayetteville or Kansas City, St. Louis, wherever, when we choose to go to a particular location, okay, I do the driving, and my wife in the passenger seat, she does the navigation. Now in the olden days, back before cell phones and cars and things like that, you just kind of had to use maps and just kind of try to figure it out. But now you can just pull up your Google Maps, and not only can you see your path, you can hit the word directions and it'll show you the direct path, and then you can hit the directions, start directions, and the lady, who is very nice, will tell you exactly how to get there, when to turn. And I don't mean she'll tell you in the fact that she just tells you all at once and you got to try to remember it. No, as you're driving along, she will tell you, hey, turn right up here 500 feet. Hey, turn right up here 200 feet. Hey, turn right up here 100 feet. In other words, she knows exactly where you are, the distance of where you're trying to get to, and can update you on when that should happen. And when you get to your turn and she says to turn right here, you are right there. And you got to think to yourself, how in the world can they know precisely where I am and precisely when I should turn, exit, stop, all that stuff? Infirmary is the answer to your question. Around the Earth, as I'm sure you're familiar with the Global Positioning System, GPS, and these 24, basically one for each time zone, satellites around the Earth. And because of that preciseness, it can tell you, can know where you are, what you're trying to, in the software, and the computer systems have gotten so sophisticated that they can tell from the images where you are, where you want to be, okay, and your path. That's interferometry. In other words, it's taking information from multiple satellites and being able to process that into not only a picture or an image, but information. Okay, information. So you can see that in Google Maps. You can see that when you look at these great images from the solar system. A lot of times they've taken multiple telescopes and gotten the image from those and put those together in order to make a great picture. When we're in the classroom, okay, we will do a visual situation or recreation of this to help you to think of this. And what we'll do in the classroom is we will put an object, okay, in the middle of that middle lab table. And we'll simply put a person in each of the four corners of our classroom, okay, and they will metaphorically either draw or describe their version of what they can see of that object. And when we take all four ideas or images, then we can get a full idea of what that entire object looks like. Any individual person can give us possibly half of it, okay, but all four together can give us a complete idea of what that object looks like. Then, if I add a fifth and sixth person, and a seventh and eighth person, we can even get even more detail because we have more images, more information coming in. That's interferometry. The use of multiple telescopes to get images. That's how you can create those 3D. If you ever go to an interactive website where you can have a 3D look at it, our A&P students do it all the time, and you can look at a particular bone or muscle or organ system, and they've even got to where you can spin them around and you can see. Okay, that's interferometry in action there. So hopefully that description gives you a good idea of what we're talking about here. And again, we will do something in class to really help you to understand interferometry. So again, remember you've got 7 things to write down. If you don't remember, be sure you go back over the list. But it's the 4 things from part 1, the 2 things from part 2, and then the interferometry definition right there. So that concludes your first video lecture. Thank you very much for watching this, for taking care of the notes, and for getting on your educational journey. And with that, we will say goodbye. Hopefully you were safe and everything is well in all these difficult times, and that you were enjoying yourself. And hope you had a great summer. And again, thank you. And with that, we will say goodbye.